Imagine if our entire galaxy, the Milky Way, wasn't moving randomly, but was being dragged through space by an unseen, colossal force. That's the mystery that began when radio observatories began noticing that distant galaxies were not sitting where quiet mathematics predicted. The light was consistently redshifted. The movement was small, yet it persisted in different directions of the sky. The strange part was its sheer consistency. No single telescope caused it. No single error explained it. The pattern remained. At first, astronomers dismissed this as a technical anomaly. Instruments were recalibrated, and atmospheric interference was scrubbed from the data. After years of repeated measurements, the pattern only became more undeniable. Vast groupings of galaxies were drifting together in one broad direction, rather than moving randomly. This kind of motion is fundamentally different from the spinning of a planet or the orbit of a moon. It is a slow, steady movement of immense structures across millions of light years. A light year is the distance light travels in 1 year, and even across that immense scale, the motion was visible as systematic shifts in galaxy positions. Imagine standing on a moving walkway at an airport for a useful, everyday comparison. A person can walk freely, stop, or change direction, but the floor itself carries everyone gently forward. In this case, galaxies behave like the traveler, while the fabric of space acts like the moving walkway. The galaxies are not propelling themselves, they are simply being carried. As more data was collected, astronomers found that this motion convergently pointed toward a single region of the sky. This region was difficult to observe directly because it lies behind the obscuring thick dust clouds of the Milky Way. Normal telescopes simply could not peer through it. However, indirect measurements showed a massive concentration of matter. The key structure behind this motion is now known as the Great Attractor. It is not a single object, but a vast region of extraordinary mass density. Mass means the amount of matter in something. When mass becomes very large, gravity becomes very strong. Gravity is the natural force that pulls objects toward each other. On a cosmic scale, this gravitational pull affects not only individual galaxies, but whole clusters of them. This collective movement is called cosmic flow. Cosmic flow describes the large-scale motion of galaxy groups moving together through space because of invisible gravitational forces. The structure of this system is immense. Billions of stars form galaxies, hundreds of galaxies form clusters. And all of these, multiple clusters, move together toward this massive region. The scale stretches across tens of millions of light years, far beyond anything visible with the human eye. The discovery of this pattern changed how scientists understand motion in the universe. Instead of seeing galaxies as isolated islands, they began to see them as parts of a single, slow, organized current. Space itself behaves like a landscape with gentle slopes, and matter naturally drifts toward the deepest regions of that landscape. This movement is not perceptible from inside Earth. The distances are enormous, and the speed is smooth and constant. Just as passengers in a smooth airplane do not feel the motion unless they look outside, humans do not sense this drift unless instruments measure it. The Great Attractor is not a single, isolated object. Rather, it is a vast region filled with an enormous concentration of matter. Matter encompasses everything that has mass, including stars, gas, dust, and the invisible, non-luminous material known as dark matter. This region sits far beyond the edge of the visible Milky Way, lying in a direction that is notoriously hard to observe because thick clouds of dust heavily block visible light. To study it, scientists rely on radio waves and infrared light, which penetrate dust more easily than visible light. The structure of this region is formed by many galaxy clusters pressed together. A galaxy cluster is a large group of galaxies bound by gravity. Gravity is the force that pulls objects with mass toward each other. When many galaxy clusters converge in one area, the resulting gravitational pull becomes immense. Think of a dense city skyline as an everyday example of this kind of effect. A single large building attracts some attention, but a dense skyline of many heavy structures radically changes the flow of wind and movement around it. In space, the Great Attractor acts like a dense skyline made of mass, profoundly shaping how entire galaxies move nearby. The natural phenomenon involved is super large-scale gravitational attraction. Stars inside galaxies orbit their centers, and galaxies inside clusters orbit their shared center. However, at this cosmic level, whole clusters are slowly pulled toward one massive region. The structure behaves like a deep valley in a flat landscape, causing everything surrounding it to slowly roll inward. The history of this discovery began when astronomers measured the motion of galaxies and noticed they were moving faster than normal cosmic expansion could explain. Cosmic expansion, the general stretching of the universe, causes distant galaxies to move away from each other over time. This unexpected extra motion strongly indicated the presence of a hidden mass. Over time, as mapping techniques improved, scientists built three-dimensional maps of galaxy positions and speeds. These maps showed a clear flow pattern pointing toward a central mass concentration. This confirmed that the Great Attractor is not a mere theoretical construct, but a structure supported by repeated empirical measurements. On a cosmic scale, this region contains mass comparable to tens of thousands of large galaxies combined. The distances are measured in tens of millions of light years. Even at this immense scale, gravity maintains its influence. The Great Attractor demonstrates that the universe is not evenly balanced. Some regions contain far more mass than others, and these differences shape the slow, steady motion of everything around them. Groups of galaxies are not drifting by accident. Their movement follows clear physical rules based on math and gravity. Mass means the amount of matter something contains. The more mass that exists in one place, the stronger its gravitational influence becomes. Gravity is the natural force that attracts objects toward each other. In small systems, this can be seen when the moon moves around Earth and Earth moves around the Sunday. These motions are stable because the mass of each object creates predictable forces. On a much larger scale, the same rule applies to galaxy groups. Entire groups of galaxies respond to the gravitational pull of massive structures in the universe. The structure of galaxy groups is layered. Individual stars group into galaxies. Galaxies gather into clusters. Clusters gather into superclusters. A supercluster is a massive collection of galaxy clusters connected through gravity. These structures span millions of light years. A light year is the distance light travels in 1 year. An everyday comparison can be found in ocean currents. A single drop of water can move freely, but when a large current forms, many drops begin to move together in a shared direction. In space, galaxy groups behave like water particles inside a slow-moving current. They maintain their local motion while drifting as a group through a larger gravitational flow. The natural phenomenon driving this movement is uneven distribution of matter in the universe. Some regions become very dense, while others remain relatively empty. Dense regions create stronger gravitational attraction. Over time, matter slowly migrates toward these dense zones, forming organized flows of motion across space. Scientists first identified this collective motion by measuring how light from distant galaxies shifted. This measurement is known as redshift. Redshift means light stretches to longer wavelengths as objects move away from the observer. By comparing expected expansion speeds with observed speeds, astronomers detected additional motion not explained by expansion alone. This discovery marked an important moment in cosmic science. It showed that the universe does not expand in a perfectly smooth way. Large-scale structures create directional movement layered on top of expansion. This combination creates complex patterns of motion across vast distances. On a cosmic scale, the distance covered by these motions is enormous. Galaxy groups can move at hundreds of kilometers per second across millions of light years. Despite this speed, the motion remains smooth and stable because it happens over extremely long periods of time. This organized movement of galaxy groups reveals that space is not static. It behaves like a dynamic environment shaped by invisible structures and gravitational landscapes that guide matter along predictable paths. The discovery of large-scale cosmic motion began with careful observation of light. When astronomers studied distant galaxies, they noticed that the light arriving at Earth was slightly stretched. This stretching is called redshift. Redshift means the light waves become longer when an object is moving away from the observer. At first, scientists expected redshift to show only the expansion of the universe. Cosmic expansion is the slow stretching of space itself, which causes distant galaxies to move away from each other over time. However, the data showed something extra. Some galaxies were moving faster or in different directions than expansion alone could explain. The structure of this research relied on large-scale sky surveys. Scientists built catalogs of galaxy positions, distances, and speeds. These catalogs acted like maps of traffic patterns in space. A normal map shows roads and cars. These cosmic maps showed galaxies and their motion through space. An everyday example of this process is tracking the movement of clouds in the sky. A single photo shows shape, but a series of photos over time shows direction and speed. In the same way, repeated measurements of galaxies over many years revealed consistent motion patterns that could not be dismissed as random. The natural phenomenon involved here is Doppler shift. Doppler shift means the change in light or sound when an object moves. A familiar example is the sound of an ambulance siren. As it approaches, the sound becomes higher. As it moves away, the sound becomes lower. With light, the shift appears as a change in color and wavelength instead of sound. The history of this discovery includes the development of better telescopes and digital detectors. Early instruments could only measure basic positions. Later, technology allowed precise measurement of galaxy speeds and distances. This improvement revealed that whole groups of galaxies shared the same directional drift. Once enough data was collected, scientists traced the direction of this shared motion. The patterns pointed to a specific region of space hidden behind the dense dust of the Milky Way. Although this region could not be directly seen, its gravitational influence could be measured by how it pulled surrounding galaxies. On a cosmic scale, this discovery required combining data from millions of light-years away. A light-year is the distance light travels in 1 year. The motions observed were not small local effects, but organized flows stretching across superclusters of galaxies. The result was a new understanding of the universe as a moving structure. Space was no longer seen as a quiet background. It became a dynamic environment where matter follows invisible paths shaped by massive hidden regions. Earth is not stationary in space. It moves as part of several layered motions that operate at different scales. Earth orbits the Sunday. The Sun moves around the center of the Milky Way galaxy. The Milky Way itself moves through a local group of galaxies. These layers of motion exist at the same time and remain stable. The structure of this movement is like a set of nested wheels. A small wheel spins inside a larger wheel, and that larger wheel turns inside an even bigger system. Each level of motion adds to the next. In space, planets, stars, galaxies, and galaxy groups behave in the same layered way. An everyday example can be found on an aeroplane. A person can walk down the aisle while the plane flies through the sky and while Earth rotates beneath it. Multiple motions overlap, yet the experience feels calm and steady. Earth's movement through space feels the same because the motion is smooth and evenly distributed. The natural phenomenon behind this motion is gravity. Gravity keeps Earth in orbit around the Sunday. Gravity keeps the Sun bound to the galaxy. Gravity also influences the slow drift of entire galaxy groups. This organized motion is not chaotic. It is guided by large-scale structures that shape the flow of matter through space. Scientists confirmed Earth's participation in this movement by measuring the speed and direction of the Milky Way. They used observations of background radiation and galaxy distributions to calculate how our local group of galaxies moves. The results showed a steady motion in the same general direction as the larger cosmic flow. The history of this understanding developed gradually. Early astronomy focused only on the motion of planets. Later research expanded the picture to stars and galaxies. Modern measurements now include motions of entire galaxy clusters and superclusters, revealing that Earth is part of a much larger pattern of movement. On a cosmic scale, the distances involved are enormous. Earth's position shifts along with structures that span millions of light years. A light year is the distance light travels in 1 year. Even across these scales, the motion remains smooth and unified. This means Earth is being carried gently within a vast cosmic current. The movement does not disturb daily life. It does not create physical sensations. It acts quietly, steadily, and predictably as part of the largest structure of motion in the universe. Massive galaxy clusters are among the largest structures held together by gravity. A galaxy cluster is a collection of hundreds or even thousands of galaxies bound by their combined mass. Mass means the amount of matter contained in an object. And when mass is very large, gravity becomes very strong. The structure of a galaxy cluster is layered. Individual stars group into galaxies. Galaxies gather into clusters. Between the galaxies, there are large amounts of hot gas and invisible material that do not emit light. This invisible material is often referred to as dark matter. Dark matter means a form of matter that does not produce light, but has mass and therefore creates gravity. An everyday example of this effect can be seen in a crowded city. A single person walking through an empty street can move freely. In a dense crowd, movement becomes influenced by the pressure and direction of the group. In space, galaxies inside a cluster behave like people in a crowd. They are free, but they are guided by the overall gravitational pull of the cluster. The natural phenomenon driving this structure is gravitational binding. Gravity pulls material inward, while motion pushes it outward. When these forces balance, a stable structure forms. Galaxy clusters achieve this balance over billions of years. The result is a slowly rotating, long-lasting system where galaxies orbit a shared center of mass. Scientists first identified the gravity of galaxy clusters by measuring the speed of galaxy movement inside them. These speeds were too fast to be explained by visible matter alone. This led to the conclusion that large amounts of invisible mass must exist to keep the clusters from flying apart. The history of this discovery marked an important shift in astrophysics. It showed that what can be seen with telescopes represents only a part of the total mass in the universe. Invisible mass plays a major role in shaping structure and movement on large scales. On a cosmic scale, galaxy clusters stretch across millions of light years. A light year is the distance light travels in 1 year. The gravitational influence of these clusters extends far beyond their visible edges, slowly guiding the motion of galaxies in surrounding regions. Massive galaxy clusters act like anchor points in space. They pull nearby matter and help define the large-scale architecture of the universe. Their gravity feeds into larger motions, contributing to the slow, organized flow of galaxies across cosmic distances. Cosmic flow describes the large-scale movement of galaxies as a group through space. This motion is not random. It follows patterns created by gravity and the uneven distribution of matter throughout the universe. Galaxies move together the way leaves move along a slow river, guided by invisible currents. The structure of cosmic flow begins with individual galaxies. Galaxies connect into clusters. Clusters link into superclusters. A supercluster is a massive network of galaxy clusters connected by gravity. These structures form long filament-like shapes that stretch across space. Between these filaments are vast empty regions called voids, where very little matter exists. An everyday comparison can be seen in a river system. Small streams join to form larger rivers. These rivers follow the shape of the land, flowing toward lower ground. In space, galaxies behave like water in a river. They follow the gravitational landscape created by dense regions of mass and avoid the empty regions. The natural phenomenon behind cosmic flow is gravitational attraction combined with cosmic expansion. Cosmic expansion means space itself slowly stretches over time. While expansion pushes galaxies away from each other in general, gravity pulls them toward dense regions locally. The balance between these forces creates flowing motion instead of simple straight-line movement. Scientists uncovered cosmic flow by measuring the velocities of large numbers of galaxies. By comparing their actual movement with the movement expected from expansion alone, astronomers identified consistent directional drifts. These observations revealed that galaxies are not just moving away from each other, but also sliding along large gravitational pathways. The history of this discovery became clearer as technology improved. Early surveys captured only small parts of the sky. Later surveys collected data from millions of galaxies. These large data sets allowed scientists to see wide patterns that only appear on very large scales. On a cosmic scale, cosmic flow stretches across tens of millions of light years. A light year is the distance light travels in 1 year. The speed of this flow is measured in hundreds of kilometers per second, yet the motion feels gentle because of the enormous distances and long time spans involved. Cosmic flow reveals that the universe behaves more like a moving landscape than a static space. Galaxies travel along invisible paths, shaped by deep structures of matter, forming a slow and organized circulation throughout the universe. Some of the most important regions of the universe are difficult to observe because they are hidden behind the Milky Way. The Milky Way contains thick clouds of gas and dust that block visible light. These clouds form a natural curtain that hides large portions of deep space from direct view. The structure of this obstruction is layered. Cold gas and microscopic dust particles spread across the disk of the galaxy. When light from distant galaxies tries to pass through these layers, much of it is absorbed or scattered. This creates a dark band across the sky, known as the zone of avoidance, where normal optical telescopes cannot see clearly. An everyday example of this effect is heavy fog. When driving through fog, distant objects appear faint or disappear entirely, even though they still exist. In space, the Milky Way's dust acts like cosmic fog, hiding large structures behind it. The natural phenomenon at work is absorption and scattering of light. Absorption means light energy is taken in by particles. Scattering means light is redirected in many directions. Together, these effects prevent clear images from forming when looking through dense regions of dust. Scientists develop methods to see through these dark regions by using radio waves and infrared light. Radio waves have long wavelengths that can pass through dust with less interference. Infrared light can also travel through dust better than visible light because of its longer wavelength. These tools allowed astronomers to detect hidden galaxies and massive structures behind the Milky Way. The history of this discovery advanced as new detectors and telescopes were built. Early astronomers simply mapped around the dark zone. Later, space-based observatories and large radio arrays began to fill in the missing areas, revealing massive galaxy clusters and dense regions of matter that could not be seen before. On a cosmic scale, these hidden regions span millions of light years. A light year is the distance light travels in 1 year. Even though they are obscured from direct view, their gravitational effects can still be measured by observing how visible galaxies move around them. These dark regions are not empty. They contain massive structures that strongly influence cosmic flow. By understanding what lies behind the Milky Way's dust, scientists gained a clearer picture of the forces shaping large-scale motion in the universe. Gravity shapes motion across the universe by pulling matter toward regions of greater mass. Gravity is the natural force that attracts objects with mass toward each other. On Earth, gravity causes objects to fall. In space, the same force controls the motion of stars, galaxies, and large-scale structures. The structure of gravity-driven motion is layered. Small objects respond to local gravitational forces, while large objects respond to powerful, distant masses. A planet orbits a star. A star orbits the center of a galaxy. A galaxy moves within a cluster. Each layer of structure follows the same simple rule. More mass creates stronger gravity. An everyday example of this effect can be seen on a sloped surface. When a marble is placed on a slightly tilted table, it slowly rolls toward the lowest point. If the table is uneven, the marble changes direction to follow the slope. In space, galaxies behave like marbles on a gently curved surface. They drift toward the deepest gravitational slopes created by massive regions. The natural phenomenon behind this behavior is gravitational potential. Gravitational potential describes how strong gravity is in a given region of space. Areas with more mass create deeper gravitational potential. Matter naturally moves toward lower potential, creating organized motion instead of chaotic wandering. Scientists observed this large-scale effect by measuring the speeds and directions of many galaxy groups. Using precise distance measurements and light analysis, they built maps showing how matter moves through space. These maps revealed that galaxies tend to flow along invisible pathways shaped by gravity. The history of this understanding developed as physics matured. Early theories treated space as mostly static. Later discoveries showed that gravity could bend light, shift time, and shape large-scale motion. Observations match these predictions, showing that gravity is not just a local force, but a universal architect of motion. On a cosmic scale, the gravitational landscape stretches across tens of millions of light years. A light year is the distance light travels in 1 year. Even across these distances, gravity works steadily, guiding matter along long, gentle curves through space. Gravity does not act suddenly at this scale. It works slowly and consistently, like a gentle current that moves everything it touches. This constant influence creates the large, smooth motion observed in galaxy groups and cosmic flow. Dark matter plays a central role in the large-scale motion of the universe. Dark matter is a form of matter that does not produce light and cannot be seen directly with telescopes. Its presence is known because it has mass, and mass creates gravity. The structure of dark matter is not smooth or evenly spread. It forms large, invisible frameworks called halos. A halo is a region of space where dark matter gathers around galaxies and galaxy clusters. These halos act like invisible skeletons that give shape to the visible universe. An everyday example of this relationship can be seen in a building under construction. Steel beams are built first, and walls are built later. The steel is often hidden behind walls, but it carries the weight of the structure. In space, dark matter acts like the hidden framework. Visible stars and gas settle into the structure created by this invisible mass. The natural phenomenon behind this process is gravitational attraction. Even though dark matter cannot be seen, its gravity influences everything around it. Galaxies rotate faster than they should, based on visible matter alone. Galaxy clusters stay together when they should drift apart. These effects reveal the presence of hidden matter. Scientists first recognized the role of dark matter by studying the rotation of galaxies. They noticed that stars far from the center moved much faster than expected. This led to the conclusion that unseen mass must be adding extra gravity. Later, similar patterns were observed in large galaxy clusters. The history of this discovery developed as more precise measurements were made. Over time, scientists mapped how galaxies bend light from objects behind them. This bending of light is called gravitational lensing. Gravitational lensing means gravity bends the path of light from distant objects, revealing the mass of invisible structures. On a cosmic scale, dark matter outweighs visible matter by a large margin. It dominates the total mass of galaxy clusters and superclusters. The distances involved span millions of light years. A light year is the distance light travels in 1 year. Dark matter does not move galaxies by force. Instead, it shapes the gravitational landscape that galaxies travel through. It creates invisible valleys and slopes in space, guiding the slow, organized flow of matter across the universe. The Milky Way galaxy is not fixed in one place. It travels through space as part of a larger structure called the local group. The local group is a small collection of galaxies bound together by gravity. This movement happens smoothly and steadily over very long periods of time. The structure of this motion begins at smaller scales. Earth moves around the Sunday, the Sun orbits the center of the Milky Way. The Milky Way moves together with nearby galaxies. All of these layers combine into a quiet, continuous journey across space. An everyday comparison can be found in a person walking on a train. The person can move freely inside the train, while the train itself moves along a track. At the same time, the Earth rotates beneath the train. Multiple motions exist at once, and none of them feel violent or disruptive. The Milky Way's movement is similar, calm, and constant. The natural phenomenon behind this journey is gravitational interaction between massive structures. Nearby galaxies pull on each other through gravity. Larger clusters of galaxies create even stronger gravitational influence. This creates a slow drift of whole galaxy systems through space. Scientists identified this motion by studying the background radiation of the universe. This radiation is a faint glow left over from the early universe. Small temperature shifts in this glow show how fast and in what direction the Milky Way is moving. These measurements confirmed that our galaxy is traveling through space at a measurable speed. The history of this discovery developed alongside improvements in telescope technology. Early astronomers believed galaxies were mostly isolated. Later research showed that galaxies live inside groups and clusters that move together. This shifted the understanding of galaxies from static islands to moving participants in large-scale flows. On a cosmic scale, the Milky Way travels across millions of light years. A light year is the distance light travels in 1 year. Even though the speed is large, the distances are so vast that the motion appears gentle and smooth. This quiet journey means that every star in the Milky Way, including the Sun and Earth, is being carried through space as part of a much larger motion. The movement is steady, predictable, and deeply embedded in the structure of the universe. The motion of Earth through space does have a relationship with time, but the effect is extremely small in daily life. Time in physics is not completely separate from motion and gravity. When an object moves very fast, or when it is deep inside a strong gravitational field, time passes at a slightly different rate compared to other places. This idea is called time dilation. Time dilation means time does not flow at exactly the same rate everywhere. The structure of Earth's motion includes several layers. Earth rotates on its axis. It orbits the Sunday. The Sun orbits the center of the Milky Way. The Milky Way moves through the local group and participates in large-scale cosmic flow. Each of these motions involves speed and gravity, which both influence time in a small way. An everyday example of this effect can be found in modern navigation systems. Satellites used for global positioning move high above Earth at high speeds. Because of their motion and weaker gravity at their altitude, time passes slightly faster for them than it does on the ground. Engineers correct for this tiny difference so that navigation remains accurate. Without this correction, position errors would grow over time. The natural phenomena responsible for these effects are special relativity and general relativity. Special relativity explains how time changes with speed. General relativity explains how time changes with gravity. In both cases, the differences become large only at extreme speeds or in very strong gravitational fields. Scientists tested these ideas using precise clocks. Identical atomic clocks were placed in different locations and on fast-moving aircraft. After careful comparison, the clocks showed small but measurable differences in time. These experiments confirmed that motion and gravity affect the flow of time. The history of this understanding began in the early 20th century with new theories of space and time. Over the following decades, experimental tests grew more accurate. Space missions, satellite technology, and high-precision timing systems all provided further confirmation. On a cosmic scale, the motion of the Milky Way and its flow toward massive structures does contribute to the overall state of time around us. However, the speeds involved, while large in kilometers per second, are still far below the speed of light. The gravitational fields experienced by Earth are also moderate compared to extreme environments like black holes or neutron stars. For daily human experience, these effects are too small to notice. Clocks on Earth remain synchronized for practical purposes, and life unfolds normally. The connection between motion, gravity, and time exists, but it operates quietly in the background, becoming important only when measured with very sensitive instruments or considered over very long periods. Earth is moving through space at several different speeds at the same time, yet human bodies do not sense this motion directly. The main reason is that these movements are smooth, constant, and shared by everything around us. There is no sudden change, no sharp acceleration, and no shifting reference point that the body can detect. The structure of this situation begins with the idea of relative motion. Relative motion means movement is always described compared to something else. Inside a steadily moving system, everything shares the same motion. On Earth, the ground, the air, the oceans, and every object around us move together through space. An everyday example is sitting on a train that moves at a constant speed on straight tracks. Inside the train, standing up, walking, or holding a cup of water feels normal. The movement of the train becomes noticeable only when it accelerates, slows down, or turns. As long as the motion is smooth and constant, the body senses no disturbance. Earth's journey through space follows the same principle. The natural phenomena involved are inertia and uniform motion. Inertia is the tendency of an object to keep moving in the same way unless a force changes it. Uniform motion means movement at a constant speed, in a straight line, or along a stable path. The forces acting on Earth are balanced in such a way that no strong jolts or abrupt shifts reach the surface. Scientists describe these ideas in the development of classical mechanics. Early studies of falling objects, pendulums, and planetary orbits led to the conclusion that steady motion cannot be detected from inside a closed system without looking outside. This insight later became part of modern physics and continues to guide how motion is understood. The history of this understanding also appears in discussions about Earth's rotation. People once argued that if Earth rotated, they would feel it or be thrown from the surface. Careful study showed that a constant rotation does not create the same sensations as sudden spinning, because everything attached to Earth shares the same motion. On a cosmic scale, the speeds involved in Earth's movement are large. Earth orbits the Sun at about tens of kilometers per second. The Sun orbits the center of the Milky Way. The entire Milky Way moves within the local group and joins larger cosmic flows. These motions stretch across millions of light years. A light year is the distance light travels in 1 year. Despite the size of these motions, the changes happen over very long time scales. The paths are smooth and the forces are balanced. The atmosphere remains attached to Earth. Oceans stay in their basins. Buildings, mountains, and people all share the same steady motion. For human senses, what matters most is change in motion, not motion itself. Sudden acceleration, impact, or vibration produces strong signals in the inner ear and muscles. In the quiet, uniform movement of Earth through space, these signals do not arise. The result is a life lived on a planet that is always moving, yet always feels still. Scientists map our position in the cosmic flow by combining distance measurements, motion data, and large-scale surveys of galaxies. The goal is to understand not only where the Milky Way is located, but also how it moves within the surrounding gravitational landscape. The structure of this mapping process begins with distance. To measure how far away a galaxy is, astronomers use methods such as standard candles. A standard candle is an object whose true brightness is well known, such as a certain type of exploding star called a supernova. By comparing the known brightness with how bright it appears from Earth, the distance can be calculated. Once distances are known, motion is studied using redshift. Redshift means the light from an object is stretched to longer wavelengths when it moves away from the observer. This effect allows scientists to measure how fast a galaxy is receding from us. By comparing the expected speed from cosmic expansion with the actual speed, any extra motion can be detected. An everyday example of this kind of analysis can be found in traffic reports. A map shows where roads are located. Speed sensors show how fast cars move along those roads. Combining both pieces of information reveals traffic patterns, such as slow zones, fast lanes, and general flow direction. In space, surveys of galaxy positions act as the map, and velocity measurements act as the speed sensors. The natural phenomena involved include Doppler shift and cosmic expansion. Doppler shift describes how light changes when an object moves, while cosmic expansion describes how space itself stretches over time. By separating these two effects in the data, scientists can isolate the movement caused by gravitational pull from massive structures. The history of cosmic mapping grew as instruments improved. Early sky charts listed only positions. Later surveys, such as redshift surveys, added velocity information. Modern projects use automated telescopes and digital detectors to collect data from millions of galaxies, building three-dimensional maps that cover large portions of the observable universe. On a cosmic scale, these maps extend across hundreds of millions of light years. A light year is the distance light travels in 1 year. The maps reveal filaments, clusters, and voids, showing where matter is concentrated and where it is sparse. They also show how galaxy groups, including our local group, move within this structure. Our position in the flow is determined by tracing backward from observed motions. The Milky Way's velocity is compared to the average motion of nearby galaxies. Deviations from this average point toward the direction and strength of the gravitational pull that guides us. When these vectors are combined, they show that we are moving toward massive regions, such as the Great Attractor. This mapping does not change our physical path, but it provides a clear, structured picture of how our galaxy participates in the larger motion of the universe. It shows that the Milky Way is not drifting alone, but is part of a carefully measured and well-defined cosmic current. Human curiosity often focuses on things that cannot be seen directly. Invisible forces invite questions about structure, cause, and meaning. Gravity, magnetism, electricity, and cosmic flow are all examples of influences that act without showing a visible shape. Their presence is revealed only through the way objects move and behave. The structure of this curiosity begins with simple observation. A dropped object falls to the ground. A compass needle turns toward a particular direction. Static electricity lifts small pieces of dust from a surface. These events repeat reliably, even before a full scientific explanation exists. The regularity of these patterns encourages careful thinking. An everyday example appears when a person feels the pull of a refrigerator magnet on a spoon. The magnet looks solid and quiet, yet the spoon jumps toward it. The force itself is not visible, only its effect. In the same way, the Great Attractor and cosmic flow cannot be seen as an object. Their existence appears in the motion of galaxies and the measured shifts in light. The natural phenomena involved include gravity and field interactions. A field is a region of space where a force can act on an object with certain properties, such as mass or electric charge. Fields do not glow or cast shadows. They are detected through their influence. This concept extends from the scale of laboratory experiments to the scale of galaxy clusters. The history of human engagement with invisible forces runs through many stages. Early explanations often often use stories or symbols to describe unseen influences. Over time, mathematics and repeatable experiments replaced stories with models that could predict events. The development of gravitational theory, electromagnetism, and later cosmology all followed this path. On a cosmic scale, curiosity about invisible forces led to measurements of redshift, gravitational lensing, and background radiation. Redshift means light stretches to longer wavelengths when an object moves away. Gravitational lensing means gravity bends the path of light. Background radiation is a faint glow that fills space and records conditions from the early universe. None of these phenomena can be touched, yet each reveals information about hidden mass and motion. Human curiosity extends beyond practical need. The motion of distant galaxies does not change daily tasks, yet it draws sustained attention. People build instruments, launch observatories, and create simulations to understand a flow that cannot be felt. This behavior shows a consistent drive to map the unseen structure of reality. This curiosity shapes the way the universe is described. Instead of thinking only in terms of visible objects, modern understanding includes fields, dark matter, and large-scale gravitational landscapes. Invisible forces are treated not as mysteries to stop thinking about, but as clues that guide deeper investigation into how the universe is organized. The cosmic flow that carries galaxy groups through space does not lead to a specific destination like a city at the end of a road. Instead, it represents the way matter moves toward regions of greater mass over very long timescales. These regions include massive galaxy clusters and superclusters that act as gravitational centers. The structure of this journey is defined by the large-scale distribution of matter in the universe. Galaxies gather into clusters. Clusters link into superclusters. Between these structures are vast, empty regions called voids, where very little matter exists. Matter tends to move away from voids and toward dense structures guided by gravity. An everyday comparison can be found in the way rainwater moves across a landscape. Drops fall randomly at first, but once on the ground, they follow slopes and channels. Small streams join to form larger flows that move toward valleys and low basins. In space, galaxies behave like rainwater. They drift along gravitational slopes toward the deepest regions in the cosmic landscape. The natural phenomena behind this motion are gravity and cosmic expansion. Gravity pulls matter inward toward dense regions. Cosmic expansion stretches space and increases the distance between structures on the largest scales. The result is a combined motion where galaxy groups both recede from each other due to expansion and slide toward massive attractors due to gravity. Scientists study the future path of this flow by using simulations. A simulation is a computer model that follows physical rules to predict how systems evolve over time. By inputting current positions, masses, and velocities of galaxy clusters, researchers calculate how these structures will move under the influence of gravity. The history of this work grew from early attempts to map galaxy distributions. As more data became available, models shifted from simple, uniform expansion to more complex patterns that included clustering and flow. Modern simulations include dark matter, dark energy, and visible matter to create a detailed picture of large-scale motion. On a cosmic scale, The distances involved extend across hundreds of millions of light years. A light year is the distance light travels in 1 year. The timescales are also immense, measured in billions of years. Over such spans, small gravitational pools accumulate, slowly changing the positions of entire galaxy systems. The direction of the current flow suggests that our local group and neighboring structures are drifting toward massive regions such as the Great Attractor and even larger concentrations beyond it. These regions are not final endpoints. As the universe continues to evolve, new structures may form, and the balance between gravity and cosmic expansion may shift. From the perspective of human life, this motion is effectively constant and unchanging. The path is long, smooth, and steady. The cosmic flow defines how matter arranges itself on the largest scales, shaping the future layout of galaxy clusters and superclusters, even though the journey remains silent and undetected in daily experience. The drifting motion of galaxies through space is part of the overall evolution of the universe. On large scales, two main influences shape this motion. One is gravity, which pulls matter together. The other is cosmic expansion, which stretches space itself. The balance between these two influences decides how the drift changes over time. The structure of the universe today shows galaxies arranged in filaments, clusters, and superclusters, separated by wide voids. Within clusters, gravity is strong enough to keep galaxies bound together. Beyond those scales, the expansion of space becomes more important. Galaxies that are not gravitationally bound move away from each other. A space expands. An everyday comparison can be found in a group of boats on the surface of a lake. Boats tied together at a dock stay close, even if the water level slowly rises. Boats that are not tied drift apart when currents or waves spread across the surface. In a similar way, galaxies bound in clusters remain together, while unbound galaxy groups drift apart due to expansion. The natural phenomena controlling the long-term drift include dark energy and gravity. Dark energy is a term used for the unknown cause of the observed acceleration of cosmic expansion. Acceleration means the rate of expansion increases over time. Gravity works to slow expansion by pulling matter together, while dark energy works to speed it up. Scientists study this balance by observing distant supernovae and mapping the large-scale structure of the universe. Supernovae are exploding stars that can act as standard candles because their true brightness is well understood. By comparing their observed brightness with their distance, researchers infer how fast the universe expanded at different epochs. These measurements show that expansion is currently accelerating. The history of this discovery marked a major shift in cosmology. Earlier models often assumed that gravity might eventually slow or even reverse expansion. The detection of accelerated expansion required adding dark energy to the standard model of the universe. This adjustment changed expectations about the future of cosmic drift. On a cosmic scale, the acceleration of expansion means that unbound galaxies move away from each other faster and faster. Over extremely long timescales, distant galaxies cross a horizon beyond which their light can no longer reach us. A horizon in this context is a limit in space and time beyond which events cannot influence an observer. Bound systems, such as galaxy clusters, remain intact under their own gravity. Inside these structures, motion continues in the form of orbits and local interactions. Outside them, the overall drift continues as space expands. The universe does not settle into a static state. Instead, it moves toward a configuration in which island-like clusters remain, while vast distances grow between them. For everyday experience on Earth, this future drift does not produce noticeable changes. The time scales are extremely long, and the processes act gently on human scales. The large-scale motion continues quietly, guided by the interplay between gravity and dark energy, without a simple stopping point in time. Cosmic flow toward the Great Attractor is not the only large-scale motion in the universe. Deep space contains several other mysterious flows, where galaxies move together in ways that simple expansion cannot fully describe. These flows reveal that the distribution of mass on the largest scales is complex and structured. The structure of these motions includes regions such as the Shapley supercluster and other massive concentrations of galaxies. A supercluster is a very large system made of many galaxy clusters connected by gravity. These structures act as additional attractors, each pulling on surrounding matter and contributing to the overall pattern of motion. An everyday comparison can be found by watching leaves on a large pond fed by several small streams. The leaves do not move in a single direction. Instead, they follow overlapping currents, shaped by the shape of the ground beneath the water and by the inflow from different sources. In space, galaxies behave like those leaves, responding to several gravitational currents at once. The natural phenomena behind these flows are the same basic forces that guide motion elsewhere: gravity, dark matter, and cosmic expansion. Gravity pulls matter toward dense regions. Dark matter provides most of the mass in galaxy clusters and superclusters. Expansion stretches the space between structures. The combination of these factors produces layered and sometimes surprising motion patterns. Scientists identified additional mysterious flows by examining galaxy velocities on larger and larger scales. After accounting for the overall expansion of the universe, they compared the remaining motions with the known positions of massive structures. Some flows aligned with visible superclusters, while others suggested the influence of mass that is still partly hidden or not fully mapped. The history of this work advanced as surveys became deeper and more complete. Early studies focused on nearby galaxies. Later projects extended to greater distances using more sensitive instruments and larger telescopes. Redshift surveys, radio observations, and infrared maps all contributed pieces of information about how galaxies move in different regions of the sky. On a cosmic scale, these flows extend across hundreds of millions of light years. A light year is the distance light travels in 1 year. The speeds involved can reach hundreds of kilometers per second. Even at these speeds, the motion remains gentle when viewed over billions of years, forming broad currents rather than sharp changes. These additional flows indicate that the universe has multiple gravitational centers of influence, not just a single dominant attractor. The Great Attractor, the Shapley supercluster, and other dense regions all play roles in shaping how galaxy groups move. Some flows may lead toward known structures, while others may hint at mass concentrations that are still being mapped. Together, These motions create a picture of the universe as a network of moving structures. Galaxies, clusters, and superclusters participate in overlapping currents guided by invisible mass and long-range gravitational forces. The result is a dynamic environment in which motion on the largest scales reflects the hidden architecture of matter in deep space. Being in motion without noticing it is a normal state in the universe. Earth, the solar system, and the Milky Way all move through space, yet daily life feels stable and still. This condition highlights how human perception focuses on local changes, while large-scale motion continues quietly in the background. The structure of this situation begins with the difference between local and global frames of reference. A frame of reference is a chosen point of view used to describe motion. Locally, the ground beneath a person appears fixed. Globally, that same ground is part of several overlapping motions, including rotation, orbit, and cosmic flow. These motions are smooth and shared by everything nearby, so they create no direct sensation. An everyday example appears when riding in a car at constant speed on a straight highway. Inside the car, objects rest calmly on the seat. A cup of water remains still. The feeling of motion fades, and attention shifts to small changes such as bumps in the road or turns in the steering wheel. Motion becomes noticeable only when acceleration, braking, or changes in direction occur. In space, Earth and the Milky Way move in a similarly steady way. The natural phenomena that allow unnoticed motion are inertia and uniform motion. Inertia is the tendency of an object to maintain its current state of motion unless a force changes it. Uniform motion describes movement at a constant speed along a stable path. When an entire environment shares the same uniform motion, internal experiences remain calm. Scientists use these ideas to build physical models that separate absolute motion from relative effects. Rather than asking if something moves in an abstract way, they describe how it moves compared to other objects and fields. This method explains why people on Earth do not feel the planet's rotation or its drift through the galaxy, even though both motions are real and measurable. The history of this understanding includes the transition from a geocentric view of the universe to a heliocentric and then galactic view. At each step, Earth's importance as a fixed center decreased. Instead, Earth became part of larger systems in motion. Observations of star positions, planetary paths, and later galaxy distributions all supported this broader picture. On a cosmic scale, the difference between experience and reality becomes even larger. The distances involved in cosmic flow reach millions of light years. A light year is the distance light travels in 1 year. The velocities involved can reach hundreds of kilometers per second. Despite these values, the slow change in position over human lifetimes keeps the motion effectively invisible to the senses. Living on a moving planet inside a moving galaxy means that stillness is relative. The feeling of rest arises from being well integrated into the surrounding motion. Buildings, oceans, air, and bodies all share the same broad trajectory through space. As a result, large-scale drift leaves no direct mark on everyday perception. What this reveals is a gap between direct experience and the underlying structure of reality. Human senses report a calm, stable environment, while measurements show layered, continuous motion. Scientific instruments and models bridge this gap, describing the quiet motion that carries Earth and its inhabitants through the wider universe. The universe is filled with motion, yet much of this activity unfolds in silence. Galaxies drift through space, clusters shift position, and large-scale flows evolve over billions of years. These processes create a dynamic environment, but the changes are spread across distances and timescales far beyond direct human perception. The structure of this quiet motion begins with the way space is organized. Matter forms stars, stars form galaxies, galaxies gather into clusters, and clusters connect into superclusters. Between these structures lie vast voids with very little matter. Each level participates in motion, guided by gravity and expansion. The overall result is a network of movement rather than a static arrangement. An everyday example appears when watching the hour hand of a clock. The hand is always moving, but the motion is slow enough that it seems still when observed for only a few seconds. Only by stepping back and comparing its position over longer intervals does the movement become obvious. In a similar way, cosmic motion is continuous, but its pace across human lifetimes appears almost frozen. The natural phenomena that support this silent motion include gravity, dark matter, and dark energy. Gravity pulls matter together and shapes the paths of galaxies. Dark matter provides most of the mass that underlies large structures, creating invisible frameworks for motion. Dark energy drives the accelerated expansion of space, gradually increasing the distances between unbound structures. Scientists study these quiet processes using light from distant objects. Light carries information about position, speed, and history. Redshift measurements show how fast galaxies move away. Gravitational lensing shows where hidden mass distorts the paths of light. Background radiation records conditions from the early universe and reveals how matter has clumped over time. The history of this understanding developed as instruments became more sensitive. Early observations revealed only a limited number of galaxies. Later surveys extended the view and uncovered patterns of clustering and flow. Space-based telescopes and large radio arrays added data from wavelengths invisible to the human eye, filling gaps behind dust and beyond the reach of optical instruments. On a cosmic scale, the distances across which this silent motion occurs reach hundreds of millions of light years. A light year is the distance light travels in 1 year. The time required for noticeable change extends into billions of years. Within such spans, galaxies shift positions, clusters merge, and flows adjust to evolving gravitational landscapes. For life on Earth, this motion forms a stable background. The planet's surface, the atmosphere, and the local environment move together as a single system. No vibration, noise, or sudden force announces the larger journey. The silence is not the absence of activity, but the result of motion distributed so widely that it never concentrates into a direct sensory event. The image that emerges is of a universe that is both active and calm. Structures move, merge, and reorganize, while local environments remain steady enough for stars to burn and planets to host life. The silence inside a moving universe is a consequence of scale, where continuous motion coexists with the appearance of stillness in everyday experience.